Hello and welcome to AzureMonk.com, and in this video we are going to be talking about Azure Kubernetes Service Networking models. In part 1 of the video, we'll talk about the Cubenet networking model. Before we begin, let's understand the AKS model at a high level. In AKS, the traditional control plane nodes are hosted by Microsoft and provided as a service. So that means you don't have to worry about the operational aspect of an API server, controller manager, etc. In Kubernetes, almost everything revolves around pods. So where do these pods run? These pods run on nodes, which in the case of AKS is a virtual machine. Now, from a networking perspective, in AKS, these pods and nodes can be deployed in two different ways, and we'll break down each of them and demystify them. The two networking models we have are Cubenet, which is also called the basic networking model, or Azure CNI, which is the advanced networking model. In both Cubenet and the Azure CNI, you can bring your own virtual network, or you can let AKS create the virtual network for you. Let's start off with Cubenet. In the case of Cubenet, every node, that is the VMs, gets an IP from the Azure Virtual Network. So what does this mean? Let's say your Azure Virtual Network has an IP space of 10.2.0.0/16, so the nodes deployed using Cubenet would reside inside of a subnet in this virtual network, let's say 10.2.1.0/24, and gets an IP address from this range. Now, the nodes themselves can talk to another resource which is connected to this network, because this is just another virtual machine created inside of an Azure Virtual Network. The connected network can be an on-prem network or an Azure network. What this also means is, let's say an on-prem resource wants to talk to the node, it can do so by using the node IP directly, that is 10.2.1.4. In other words, this is a real and routable IP. Great. But we all know in Kubernetes, pods are the basic building blocks, and pods run inside of nodes. In the case of Cubenet, the pods themselves don't receive an IP from the virtual network. They get their IP from a logically different address space. This IP address is defined during the cluster creation process with the variable pod_cider. This is usually a large address space which does not overlap with an on-prem or a connected virtual network range. Let's say, for example, 10.244.0.0/16. Now this pod_cider is broken down into several /24 ranges. That is 10.244.1.0/24 and 10.244.2.0/24 and so on. And each of these /24 address range is assigned to every node in the AKS cluster. What that means is every pod that gets created within node 1 would get an IP address range from 10.244.1.0/24, and every pod which gets created on node 2 gets an address range from 10.244.2.0/24 and so on. If the pods get a separate IP address range, how do they talk to other pods? Well, they can talk to the other pods by using IP forwarding and user-defined routes. If you're not familiar with route tables and routing in Azure, I would highly recommend you check out the super simplified explanation of Azure routing by clicking on the link above. So, when an AKS cluster is created using Cubenet, and if the subnet doesn't already have route tables, it automatically creates one for you. But if you already are using a route table, then AKS only adds the relevant routes to the existing route table, which looks like this. Well, what this means is, if you need to go to 10.244.1.0/24 as the destination, or in other words, if you're looking to reach any of the pods which belong to node 1, you take your next hop as the node 1 IP address. Similarly for other nodes. So if a pod from node 1 needs to talk to another pod in node 2, it takes an additional hop to reach the pod in node 2, which adds minor latency to the pod-to-pod communication. Well, this is great and works well with the pod-to-pod communication. But what happens if the pod tries to reach another resource in the connected virtual network or on-premise? We know the pod IP is not from a routable range. So when we try to reach a resource outside of the pod space, it's going to fail. However, with AKS Kubenet, this communication is made possible by translating the source IP of the pod to the node IP address, or network address translating or NATing. This way, let's say a web pod needs to talk to a database server hosted elsewhere on the network, be it on-premise or another Azure connected virtual network, it can do so by NATing. If we need to come the other way around, let's say for example, the database server needs to talk to the pod IP directly, that would not be possible with the Kubenet networking model. However, there are other ways to resolve this using services and ingress controller, which we'll cover in the later upcoming videos. Okay, this sounds great, but what's the catch? There are certain limitations that we need to be mindful of with the Kubenet deployment. Number one, there can only be one cluster per subnet. You cannot create multiple AKS clusters in the same subnet. Number two, if you remember from before, every time a pod needs to talk to another pod hosted on another node, there is an additional hop which causes latency. Number three, Kubenet doesn't support Azure network policies, Windows nodes, or virtual nodes. We'll cover all of these in the upcoming videos. And the fourth point is managing user-defined routes can get complex for larger clusters. So why would you want to use Kubenet? Let's say your organization is running out of allocatable IP addresses, then Kubenet is a great solution for you because like we know, in Kubenet, the pods don't get a real IP address range from your network. If you have an AKS cluster, which restricts most of the communication to pod communication within the cluster itself, then Kubenet is a great solution as well. In the next video, we'll address how Azure CNI networking model solves some of the challenges of user-defined route management and other communication limitations. Thank you for watching. I'll see you again in the next video.